This is Chapter 16, Lecture 2. We'll pick up now with levees. These are natural levees. And how do they form? Well, a levee is a raised embankment commonly seen on both sides of a stream. It has sediment similar to the material in the channel. It's going to be coarser than a floodplain. So during a flood, sediment carrying water spills out of the channel and deposits sediment beside the channel as the water spreads out and slows down. And you get these raised features here. So we see in a flood, the water spills out and deposits sediments. You've probably heard more about constructed levees, such as in the Mississippi River Delta, New Orleans area. Those are meant to keep water in the stream during flood events. And they can trap flood waters in if a levee is breached or overtopped during a flood. A natural levee could work the same way, depending on the situation. So let's look at the Mississippi River Delta. Parts of New Orleans are below sea level. They are meant to be protected by constructed levees. If the levees are breached, then we have a whole lot of trouble in this area, and we have had that in the past, of course. Okay, I want to talk more about that, but we're going to go into sediment deposition in a delta. So, you know by now that rivers carry sediment, and as they reach, say, the mouth of the river in a larger body of water, the stream slows, deposits sediment, and then spreads out. And that's at base level. And that can clog channels and then spread out further like this. That's kind of like how the Mississippi River Delta is. Some sediment is going to be deposited on low areas next to the stream. And then if you were to cut through a cross section of this area, you'll see horizontal beds on top of the delta. And then inclined beds along the front. And then flat beds of silt and clay further out. So this is the sequence that we would expect in a deltaic system. You've got flat, inclined, and then flat layers kind of alternating. So when a stream approaches base level, we'll look at the Nile River. It has a delta that spreads out in a fan shape. The Nile River spreads out at base level and deposits that delta. Over here is the Lena River in Siberia. It splits into many channels on the delta into a distributary system, kind of like the Yukon River Delta was in the first lecture. In the winter, the sea freezes and sea ice stops the surface flow, which traps sediment along the land-sea interface. So you can see how we don't have, winter acting that way in Egypt along the Nile. So we have this nice fan shape without a lot of complexity compared to the Lena River. Now let's talk about damming of a river. Okay, so you have a stream flowing out. This is a man-made structure that stops the water, creates a larger body of water, and it can drain further like this. So the dam represents a new temporary base level for a stream. New temporary base level. And we have sediment deposition right in front of it. A delta that sort of builds into this reservoir of water. And clear and cold water can then be released from the dam, unlike this pre-dam flow. Dams are often built for flood control, power generation, water storage, recreation, and other uses. but there can be consequences. And we know that in mid-Michigan, they can be sites of flooding. The dams can fail catastrophically. They can also lose more water to evaporation. Stream would no longer carry sediment downstream to replenish nutrients on the floodplain. And then a lot of silt added to this area can sort of shorten the life of the reservoir that was created in the first place. So dams need to be managed properly. We'll go back to the lower Mississippi River and just think about the sediments here associated with that. Anything in gray, I'll point that out, is recent sediment. These yellow-orange rocks are older sediments, and even older than that would be the other colors. We have a cross-section through that, through Memphis actually. It shows that this river that we have now is above an older structural trough, like a low point. So flow was preferential through that area due to the existing structure that we have from the Paleogene and Cretaceous on top of the Paleozoic materials. And that became this huge drainage area. So we'll go back as well. Before 15,000 years ago, ice covered this region and the river didn't exist. Let's see. When the ice ages ended, melting of those ice sheets uncovered the region, increased discharge, and established the upper Mississippi River system. Of course, I'll point out that the Great Lakes region as well was covered in ice. So we had that here, and then a lot of melting, and then that water had to go somewhere. All right. I mentioned before the fall line associated with the Piedmont and the coastal plain. So that's the Appalachians and Baltimore through Richmond, Virginia. The fall line is a line of waterfalls found at the boundary of hard rock to the west and soft sediment to the east associated with the Appalachians. And many early settlements, and I don't know how early we're talking, but many settlements were along this line. Let's say European settlements, because they used the waterfalls for mills to turn their equipment. Okay. So what conditions can change streams? Many different things. Let's say with ice sheets. Those lower sea level and depress the Earth's crust, and then streams can flow toward ice. Melting ice sheets release water, and they take weight off the crust. And then streams would therefore flow away from that uplift. Tectonic activity can uplift mountains and increase the supply of sediment to an area. And then, of course, uplifted regions change precipitation patterns in terms of heavy precipitation on the upwind side of a mountain and a rain shadow on the downwind side. And that can all affect the flow of water and the conditions acting on streams. Climate also obviously affects streams. So we have a stream from before 1880, right? A stream on a floodplain. Say it's an early stream flowing on a broad valley. Let's see. European settlers in the southwest U.S. found streams flowing on broad valleys, but by 1880, changes in climate caused the streams to incise, leaving the previous floodplain as a dry terrace above the new incised channel. And we show that here. Around 1940, this same area would have a channel beginning to deposit sediment and build back up again on either side. All right, I skipped ahead a little bit. So that's something that could affect the way life is supported in that area, the way agriculture is supported, the ability to eat, obviously, depends on the state of a stream, which is affected by changes in climate. Okay, so stream terraces. Many streams can be flanked by relatively flat benches, such as these that we call terraces. So we have 1, 2, 3, and then a floodplain right next to a stream. This is our active channel in the modern floodplain. And we go from the highest terrace on this side to the middle, you know, back down to the lowest terrace and the floodplain. So the formation of these could be as such. You've got an early stream that's level with its floodplain. Over time, the stream downcuts and forms a new lower floodplain. And then there's a terrace left behind. The stream continues downcutting, which leaves each previous floodplain as a terrace above the stream. So understand that the highest terrace formed first, followed by each successively lower terrace. And then entrenched meanders. Again, an early stream is level with the floodplain. The stream over time cuts into, say, hard rock, entrenching this river into a canyon. Over time, incision of that stream deepens a canyon, but the original meander shapes are preserved. So this is in hard material versus, say, softer material that could result in terraces. Streams can also cut across geologic structures, such as this large anticline. This is the Green River. It flows across the fold. So why is that? The Green River flows south. It cuts across the large anticline at Split Mountain, and that's in Dinosaur National Park in Utah. So either the fold grew after the river or the fold was not exposed when the river eroded down. The interpretation that we have is that the fold formed first, but it was covered by soft sediment through which the river eroded and later encountered hard rocks in the center of the fold. These are all images of what we can call a natural bridge. Okay, and they can be over a stream, they can be bridge or arch-like, and they can have, I don't know, something we can't describe so easily. We'll just call that a diverse formation. So natural bridges form in canyons, usually with a curved aspect. Streams erode to form deeper canyons, like as in an entrenched meander. Eventually, some of those meanders are cut off by the stream, forming an abandoned meander. And the stream erodes only at river level, so a natural bridge forms. You can kind of see that here. Natural arches, okay? So you could have an opening in a rock. You could have something through a narrow fin, or you could have elliptical joints, as in this photo. So arches require a strong rock to begin with one or more sets of joints present. And then weathering and erosion widen and deepen the joints over time. With enough time, narrow fins of rock form, and then arches can form with even more time. We see that here. Let's talk about floods again. So what is and is not a flood? Something is not a flood if water stays within a stream channel, unless flow within that channel causes a lot of erosion and destruction of a bank. Most flooding involves a stream overfilling its channel and spilling onto the known floodplain. We talked about constructed levees. Those can keep moderate flows within the channel. And flooding can furthermore expand the floodplain by carving the channel and burying older materials. We can graph that. So we can graph floods and non-flood stream flow. So discharge over time. Remember that a non-flood flow stays within the channel below flood stage. Here's flood stage. We're not flooding here. We just got stream flow as such. Flooding can be a slow or a rapid increase in the discharge. The only thing is that it must exceed what we denote as the flood stage. So this one is slow and gentle. This one is rapid. If this time is in days, this one is like a flash flood. If it's in months, then this could have been depicting quick and high snow melt. This will be an exploration of the 1993 Mississippi flood. So in this case, flooding built up over a period of several days to weeks, but continued for 2 months. We had a situation where cold air and warm air collided, causing persistent thunderstorms. So a little bit of meteorology here. Before flooding, it looked something like this. Okay. And during flooding, all this water was flowing through the area. We've got a discharge over time graph here. You can see it's relatively complex. Okay, so discharge was higher than normal for several months. We saw the beginning of the flood event right here. All right. And it just continued to go up under these conditions. And it peaked here, but there were upstream levee breaks, which provided for the discharge to go down for a little bit, but then peak again, because it's like the water went elsewhere for a little bit onto the floodplain where we don't quite want it, right? And then as the flood event was ending, we see an overall decrease in discharge and an increase up through September again. We'll also look at this one, the 1976 Big Thompson flood. So you had here a stationary thunderstorm. That's where cold winds pushed moist air upslope, forming that thunderstorm. And these blues here are showing the highest rainfall over the Big Thompson River. That resulted in a very quick flash flood that killed people who were just camping in the area, and it destroyed buildings. So that one happened very quickly rather than the one previously described that took months to build up and dissipate. So how do we measure and calculate flow? The volume of water flowing through a channel over a given time is discharge. Okay. So we're looking at a stream cross-section here. So for a stream discharge, you can calculate the cross-section, from the cross-section here, depth times width of water, and then how fast the water is flowing. That's the velocity. Each of these squares is representing 1 meter by 1 meter. If velocity is 1.1 meters per second, you can use that information to calculate the discharge for this stream. And the answer would be 11 cubic meters per second. You can also calculate what discharge is needed to fill a channel that is 10.5 meters wide, where velocity is 1.5 meters per second. The answer for that would be 31.5 cubic meters per second, or 30 if you use 10 meters wide. All right. Discharge during a flood. More on that. So, stream discharge is small and consistent before a flood. We see a gradual increase in discharge during and after a storm, with the highest discharge at the peak flood, and then it returns to normal discharge after the storm and flood pass. Pretty simple. We can use past flow data, discharge data, to look at the probability that a flood will occur. And this is a graph for the Verde River of Arizona. What's the largest recorded flood on the stream? Well, it's right here, above 4,000 meters cubed per second, cubic meters per second. If we were asking this in 1990, we'd say our largest recorded flood was about here. That was under 3,000 meters cubed per second. This is a graph of flow probability for the same stretch of river. We can ask what's the probability in percent each year that the stream flow will reach 2,000 meters cubed per second. Okay, so we really don't have that here. We have, great, almost 100% probability that we'll have this amount of discharge, right? But if we go up to 2,000, that's somewhere here, the probability is very low, like less than 1%. Probably that the stream flow will reach that particular number. This is kind of a sure thing. This becomes less and less probable. Something very strange would have to happen. But it could happen. So with that, we'll stop here for this chapter.